Okay, hi everybody, I'm back again. We're going to look in this lesson on using angle bisectors of triangles. So for this video I just captured a lot of information from your text. I'm just going to add a little bit to that, but mostly it's just information from your textbooks. If you want to look there, you certainly can. So, of course, an angle bisector is a ray that comes from the vertex of the angle, comes out, and then bisects that angle. So if we know AD is an angle bisector, then we know that angle BAD is congruent to angle CAD. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So if AD is the bisector of BAC, and this is important, that segment DB is perpendicular to ray AB and DC is perpendicular to ray AC. So it's not just any old line segment going from point D to ray AB. It's the perpendicular segment. In other words, it's the way to calculate distance from this point to this line, or this ray. It's always a perpendicular segment. But if D is on the bisector, then it's equidistant. Or again, in other words, distance DB is equal to distance DC, and of course segment DB is congruent to segment DC. The converse, we can just flip that. We're going to flip the if and then. So if a point is in the interior of an angle, and if we know it's equidistant from the sides of the angle, then it lies on the bisector of the angle. Just a reminder that when we're in chapter 5, we're going to write the shortcut and then in parentheses write the if then, until we get these things internalized. So again, now we know we have this segment congruence here, DB and DC, or we have equidistance. So, and these are perpendicular, don't forget that. Then we know D lies on the perpendicular bisector of the angle. So here's a problem applying the theorem. So we need to find measure of angle GFJ. So in this diagram, we're given distance JG is 7. So that's the distance from this point to this ray, because it's a perpendicular segment. We're given that as 7, and we're given the distance JH is also 7. Okay, so that's equidistant. So then I know ray FJ is the angle bisector. So then I know segment GFJ, measure of GFJ, equals measure of HFJ, and they're both 42 degrees. We're going to use an algebraic problem here. So it says, for what value of x does P lie on the bisector of A? Because of the converse, that we know that P lies on the bisector of A if P is equidistant from the sides. So when BP equals CP. So we just have to set these two algebraic expressions equal to each other and solve for x. Finally, there's one other new vocabulary word and a special point that these angle bisectors make. The theorem is concurrency of angle bisectors of a triangle. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So if these red lines, so if segment BP and segment AP and segment CP, those are the three angle bisectors, they cut each of those angles in half. The point where they meet up, that point of concurrency, if I drop down perpendicular segments to the sides of the triangle, or in other words, find the distance from point P to each side of the triangle, those distances are all equal. And those segments are all congruent, right? PD, segment PE, and segment PF are all congruent, and their distances are equal. And this other new vocabulary word here is then that special point, P, when we're talking about concurrency of angle bisectors, the name of that point is the incenter of the triangle. And it always lies inside the triangle.